Okay, so did you try to solve this? Did either of you try to solve this? And you can be honest, no? If you didn't, it's okay. Wala bang feedback? Hello? Yeah, did you try to solve this, Albert? Nasubukan mo ba i-solve?
Sir, hindi lang po lahat.
Okay. Sige, no? So let me go through this problem, ano? Because this problem will illustrate certain considerations that you have to make, ano? Okay, so first of all, let's try to design the circuit using diode logic. Okay, so I have here an OR gate. I have here another OR gate. Okay, so diode logic. So this is my first OR gate. Okay. And then this is my second OR gate. Okay. So yung isang input from each of the OR gates will share, rather, no, A is fed into both inputs of the A is fed into both OR gates, no, basically. No? So I have this one shorted here, then I have A fed here, no? And then I have B on top and C below, no? B on top and C below. Okay, let me call this R1 and R1. No? Okay, then I have a two-input AND gate. So ano yung diode logic natin sa AND gate? Okay. Yan, ano? Let me call this R2. Let's say I feed this with VCC. Okay. So yung output ng isang OR gate papasok sa input ng AND gate, and then yung output dito sa OR gate na to papasok dito sa AND gate. So essentially that's the solution. Okay. Okay. The problem here is you have to consider the proper values for R1 and R2. No? Okay, bakit? Ano? Okay, so for example, no, let's say both A and B both be 0 volts. Okay, A and B both be 0 volts. So if A and B are both 0 volts, then this is equivalent to an open circuit. Okay. Sige, gawin na natin sa lahat, ano? Sorry, no, if I'm a little bit disorganized. Okay, so let A, B, and C all be 0 volts. Okay, so if A, B, and C are all 0 volts, in effect, grounded lahat to, these are all grounded, no? Then none of these diodes will be conducting. No? So what's going to happen? So all the OR gate diodes will not be conducting. No? Therefore, this will be equivalent to open circuits. So anong magiging equivalent circuit ko? Okay, my equivalent circuit, I'm going to have VCC. Then I'm going to have R2. Okay. Then I have a diode here, R1. And then I have another diode here. And then another R1. No? Now, where is my output? My output is here. This is V sub O. Okay, what logic level is V sub O supposed to be? No? Can you answer my question? When A, B, and C are all zero, ano dapat yung logic level ng V sub O? Going back to this. Okay, it's going to be zero, no? When A, B, and C are all zero, then V sub O is going to be zero. So dapat mababa yung voltahe natin dito. Right? Now, how do I compute for V sub O here? No? So using nodal analysis, okay, using nodal analysis, okay, V sub O minus VCC over R1, okay, that's this current, the current flowing up here, okay, plus V sub O minus 0.7, so let's say this is silicon, no? So if this is silicon, first of all, we can see that this diode should be conducting, no? As long as VCC is greater than 0.7, then this diode will be conducting. So V sub O minus 0.7 over R2 to, no? This is R2. Okay, VCC minus 0.7 over R1 plus another V sub O minus 0.7 over R1, no? Because you have a current here and then you also have a current here. No? So actually this is multiplied by 2. This is equal to 0. Okay, so V sub O is supposed to be logic level 0. That is, if this output is to act as an input to another diode logic gate, it should not allow, for example, if it acts as input to another diode logic OR gate, it should not allow this to turn on, right? It should not allow this to turn on. Okay, so the values of R2 and R1 have to be properly selected. Okay, so that V sub O is a logic level 0. No? Usually, you make R2 large, and then you make R1 small. So dapat dito, itong R2 malaki, yung R1 maliit. Okay? So pag dinignan mo, pag yung R2 malaki, yung R1 maliit, okay, then the voltage drop across R1 would be small. You add to that this 0.7 volts, and that should be V sub O. Okay, let's take up the RTL inverter. No? So, in effect, here, no? So we already discussed diode logic. So in diode logic, you can only implement AND and OR. So let's go to resistor transistor logic. Okay. So the first thing that we will take for resistor transistor logic is your inverter. Now, this is going to be the circuit of a simple RTL inverter. Okay. Notice it's the circuit of a BJT amplifier, no? Except that you operate either in cutoff or in saturation. If you are in cutoff an input voltage of 0 will cause no collector current to flow, and therefore your output voltage will be 5 volts. If your input is 5 volts, on the other hand, no, we're assuming that 5 volts, your supply voltage, is also your high level input voltage, or your input voltage equivalent to a logic level 1. So if your input is equal to 5 volts, then, okay, you must properly select the values of RC, RB, and the beta of the transistor so that your transistor will be saturated. And at saturation, your output is 0.2 volts. In other words, this is actually still equivalent to a logic level 0, no? Because if you input a logic level 1, the output should be a logic level 0. Actually, itong 0.2 volts is quite close to 0 volts, the nominal logic level 0 voltage. Okay, so let's consider this case. We have RC equal to 1K and RB is equal to 10K. So my question is, what is the minimum beta, okay, for this RTL inverter? When RC is equal to 1K and RB is equal to 10K, no? Can you do that? Can you take 2 or 3 minutes to tell me what the answer should be? What is the minimum beta for this for this transistor? No? What is the minimum beta so that these are my characteristics? Then once you've done it, please chat me your answer. Okay, this is also a good review for your exam, no? Your BJT exam. It's a very simple solution, no? Okay, anybody with an answer? Anyone? Are you even trying?
Yes, sir.
Okay. Ano yung sagot, Albert? No. I'm asking for the minimum, not a value that will work, no. I'm asking ano yung minimum beta para itong transistor na to, itong transistor na to will act as an inverter for RC equal to 1K and RB equal to 10K. What about Mel? Have you tried? Meron ka na bang sagot?
Yes, sir. Ay, hindi, wala pa po, sir. Pero nagtatry po.
Oh, sige. Anyway, sige, let's just do it, let me add a page, no? Okay, what is the minimum beta, no? Okay, what is IC SAT, ano? This is going to be IC SAT. Okay. IC SAT is equal to 5 minus VCE SAT, but VCE SAT is 0.2, no? Minus 0.2 all over 1K. And this is going to be 4.8 MA. Okay. Now, for IC to be equal to IC SAT, your IB should be greater than or equal to IC SAT over beta. If I want my current here to be saturated, then my base current here, IB, should be greater than or equal to IC SAT divided by beta. No? Because remember that when your beta exceeds that value, yung IC mo will now stay constant already at IC SAT. Ano? Okay, so IB should be greater than or equal to 4.8 MA over beta. Okay, but what is IB? No, what is my formula for IB? But IB is equal to 5 minus 0.7, 5 volts minus 0.7 over 10K. No? So 5, no, I'll continue. No? So 5 minus 0.7 over 10K should be greater than or equal to 4.8 MA over beta. If I solve for beta, beta should be greater than or equal to, and I have the answer somewhere here, about 11.2. Beta should be greater than or equal to 11.2. Okay, which is actually not a large beta. Kasi typically yung mga beta ng mga transistors anywhere from 50 to 100, no, even to 200, ano. Yung 11.2 medyo maliit na beta yan, no. In fact, you only see very low betas for power transistors. Typically yung mga small signal transistors natin would have a much larger beta in the range of about 100 plus. Meaning to say, almost sure that if I put any transistor here, it's going to act as an inverter. Okay, maybe another interesting question, ano? So let's assume beta is equal to 50, no? So what range of input will be considered A1, also assuming 5 volts is the maximum input voltage. Because usually our input voltage is limited by our power supply. So assuming 5 volts is our maximum input voltage, no? If we have a beta equal to 50, what range of input will be considered a logic level 1? Okay, again, no, going back here, no, VI minus 0.7 here over RB, that is IB. No? So IB is equal to VI, that is my input, minus 0.7 over RB. RB is equal to 10K. Okay, and IB, we said, should be greater than or equal to 4.8 MA over beta. So ito yun, ano? here, no? IB should be greater than or equal to 4.8 MA over beta, but we said that beta is equal to 50. So I have VI minus 0.7 over 10K should be greater than or equal to 4.8 MA over 50. Okay, solving for VI from here, no, should now be greater than or equal to 1.66 volts if you solve for VI. So ano ang logic 1, no? Your logic 1 should therefore be VI anywhere from 1.66 volts to 5 volts. Because we assume that 5 volts is the maximum input voltage. So if I input any voltage from 1.66 volts to 5 volts, that will be recognized by my inverter as a logic level 1, no? Meaning to say my output will be 0.2 volts. 0.2 volts. Okay. So what will be my logic level 0? Can you tell me what will be my logic level 0 for VI? Ano ito?
Anything below 1.66 volts, sir?
No.
From
Zero, your input 0 is what is needed for this transistor to be cut off. No? So, having said that, ano dapat ang logic level 0 ko? Kailangan cut off tong transistor na to.
Ano po sir? 0 to 0.7 volts?
That's right, no? So ang minimum value ng VI is 0, syempre kasi yun yung pinakamaliit na voltage natin, that is our reference voltage, and then hanggang 0.7 volts. So ito yung logic level 1, ito yung logic level 0, no? So don't make that mistake, no, na anything below 1.66. Remember, meron tayong forbidden range, di ba? Nung kinuha natin yung let me go to that, saan ba yun? Here, no? Okay. So ito yung input range natin ng, for example, if this is our characteristic curve, no, our transfer characteristic curve, ito yung range natin ng input 0, ito yung range natin ng input 1, no? Ng input 1. So when my input is 0, my output is 1. When my input is 1, my output is 0, mababa, no? And then ito yung tinatawag na undefined logic state. Undefined logic state. So, ganun din yung sa example ko, no? Basically, ang magiging undefined logic state ko in this particular case is anything from 0.7 to 1.66. That becomes my undefined logic state. It's from 0.7 to 1.66 volts. Ngayon, kailangan check-in din natin, yung 0.2, kasi dapat yung output nitong gate na to, can be used as input to another gate, So this is supposed to be a logic level 0. Okay lang, kasi ang logic level 0 is anywhere from 0 to 0.7. So this will work as a logic level 0, yung 0.2. Right? So that's you always have to check that the output of your gate, will work at its proper logic level if it is input to exactly the same gate. Okay. So that's the RTL inverter. Now, this is the RTL NOR gate. The RTL NOR gate. So ang RTL NOR gate, ang base circuit niya is an inverter, pero dadagdagan natin ng one similar transistor in parallel, no? So magkakaroon ka ng, this is a 2-input NOR gate. Magkakaroon ka ng dalawang transistor ngayon in parallel. Okay? So notice that when both inputs are 0, so dito, then both of these are cut off, and therefore yung output natin will just be equal to 5 volts. Because both our transistors will be cut off, no? Hanggang anong voltage pwede yon? Hanggang 0.7, no? In this particular example, hanggang 0.7. Kasi hanggang 0.7, cut off yung Q1, cut off yung Q2. So 5 volts pa rin yung output, no? Now, if any of the voltages here is 5 volts or is logic level 1, I want to say, no, if any of the inputs here is a logic level 1, now here, in this example, it's 5 volts, but it doesn't have to be 5 volts, no? Like here, we said it can be as low as 1.66. No, in this particular case, it will not be as low as 1.66. No, and the reason for that is when both of these are conducting, then the current flowing through here is going to be shared by the two transistors. Okay? So may corresponding computation yan for IB. Now, if one or two conduct, no, then it's going to be, the output is going to be 0.2. But the minimum voltage that will be accepted as a logic level 1 should be computed based on itong current na to, no? Let's call this IX, no? On IX being shared by Q1 and Q2. No? In other words, if both A and B, no, if both A and B is, if this is 5 volts and this is also 5 volts, this is going to be IX over 2, no, and this is also going to be IX over 2. Okay? So ang computation natin for the minimum beta, for example, will be based on IX over 2. It's not going to be based on IX. Okay? And then if you have a 3-input NOR gate, so 3-input NOR gate, so dadagdagan mo pa na isang transistor, then this current is now going to be shared by 3. And therefore, our minimum beta for this transistor will now be based on IX over 3, and so forth. Okay? But when you have any of the transistors conducting or any of the transistors saturated, then your output will just be 0.2 volts. Any questions with regard to this? Okay, so you see that a NOR is easier to implement than an OR. For an OR gate, you need 2 transistors. An OR gate is actually an OR gate with an inverter. So pag nagkabit ako ng inverter dito sa output, no? So I connect this here to the output, then that's when it becomes an OR. That's why your natural gates in RTL are your NOR and also your NAND. These are your natural gates, no? To produce an OR and an AND, you have to put an inverter at the output of your NOR or your NAND. Okay, so ito yung circuit ng NAND gate. This time what you do is you put your two transistors in series. Okay? You put your two transistors here in series. Okay, and you rely on your input voltage here, putting both these transistors in saturation so that you get this combination. And when both these transistors are in saturation, then the voltage across both transistors will be 0.2 volts. So your output is going to be 0.4 volts. Okay, your computation for the minimum values of A and B to make to be considered in a high input voltage becomes a little bit more complicated now, no? Because VCE of Q1, no, has to subtract the VCE of Q2 from the KVL of the collector circuit. So yung VCE nila naka-series, no, hindi naka-parallel. So that's again another exercise that you can do, no? But the thing here now is this, no? Whatever current here, that's your current here, and that's also your current there. Okay. Note that I have VBE here. I have VBE here. Okay. If I compute for, let's say, IB1, no, my IB1 will be equal to VA minus VBE minus VCE2 all over RB1. VA minus VBE minus VCE2 over RB1. Samantalang yung IB2 ko will just be VB minus VBE over RB2. So iba yung formula ko for IB1, iba yung formula ko for IB2. So I'm going to get, if I had to compute for the minimum value of VA, it will be different from the minimum value of VB. Okay, and therefore you should always go for the worst case. Always go for the worst case. In other words, the smaller of the two, or the larger of the two, would be your logic level 1, your valid logic level 1. Now the other issue with your NAND gate is, okay, no? Remember the output of your NAND gate should be a valid input to a similar gate. Output of your NAND gate should be a valid input to a similar gate. So if I have a three input NAND gate, no, when all inputs are 1, my output will be equal to 0.6 volts. Kasi tatlo na yung naka-series. Okay. If I have a 4-input NAND gate, no, my output will be equal to 0.8 volts. Now this is going to be a problem. Okay, why will this be a problem? Can either of you tell me? Bakit magiging problema yung 0.8 volts?
Kasi sir, mawawala na po sa cutoff.
Ano yan? Ano yan?
Mawawala na po sa cutoff.
That's right,
Po,
exactly. No?
lalagpas na po sa
So,
0.7.
so kung gagamitin mo ngayon tong output na to as an input to a similar gate, sabihin natin, no, itong output na to, i-input natin dito sa B, magka-cut in na tong transistor na to. And therefore, it's no longer recognized as a 0 volt. No? So that's why this is a problem. No? This is no longer a 0. So those are the nuances of these implementations. Okay. So nakuha na natin yung RTL, no, resistor transistor logic. Now let's go to NMOS, no. NMOS logic actually consists of NMOS transistors and resistors. Okay. So this is the circuit of a simple NMOS inverter. No? Again, it looks like a NMOS amplifier, a common source amplifier, except that we operate this in either cutoff or linear. Cutoff or linear. In cutoff, nominal input voltage cutoff, or the nominal zero input is a 0 volts. Okay, there's going to be no current, no drain current, and therefore VO is going to just be equal to VDD. In linear, the assumption is V sub I is large enough. This is in linear mode. It's going to be equivalent to a resistance, RDS on. And that resistance will be very much smaller than 500. No? Will be very much smaller than R. So that, no, if I get the output, okay, using voltage divider, no, so 5 times 10 divided by 510, that's going to be approximately equal to 0.05. Sorry, mali, ano? No, this is wrong, no? It should be approximately equal to 0.01, 0.1, no? Yeah. Approximately equal to 0.1. Sorry, no? Mali ito. No? Because VO is equal to 5 times 10 all over 500 plus 10. No? If you wanted to be exact about it, okay, that's about 0.098. No? Okay. Okay, actually, what is RDS on? No? In this particular case, RDS on, this is approximately equal to 1 over K VGS minus VTH. No? Now, VGS happens to be 5. No? So that's why we got 10. No? So this is approximately equal to 1 over 25M, sorry, 25M. Then 5 minus 1, this is 4. No? That's what we got. We got, no? 10 ohms. Okay, what if I did not use RDS on? Ano kung hindi ko ginamit yung RDS on, no? So what if I used the linear equation for the NMOS? Okay, so what is that equation? No? Ito yung ID. ID is equal to K VGS minus VTH minus VDS over 2 times VDS. Ano? So what is that? That's 25. VGS is 5. So this is 5. This is 1. So this is 4 minus VDS over 2 times VDS. Okay. Or this is, yeah, 100 minus 12.5 VDS times VDS. But then ID is also equal to VDD minus VDS over R. No? So in this particular case, ID is equal to VDD is 5 minus VDS all over 500. So I equate these two. Okay. If I solve for VDS, and you can do this, this ends up being a quadratic equation with two roots. You eliminate the root that is not in the linear region. If you solve for VDS, and I have the answer somewhere here, no? Yeah, I'm going to get VDS is equal to 0.099 volts. No? So if I look, no, if I look at this and I look at this, halos pareho lang, no? Almost equal. Meaning to say, in this particular case, when we use the RDS on approximation, because this is only an approximation, we use this. Actually, RDS on, if you take a look at your notes, RDS on is equal to 1 over K VGS minus VTH minus VDS over 2. Minus VDS over 2. Okay, but we don't know the value of VDS. But we know that it is small, usually very small, compared to VGS minus VTH. And that's why we said that this is approximately equal to 1 over K VGS minus VTH. Right? So when we use this approximation, we came up with VO equal to 0.098. When we use the actual linear equation, we came up with VDS, which is VO. No? This is VO. No? This is our output, which is VDS, equal to 0.099. No? So kita mo halos pareho. Meaning to say, this is a very good approximation. But this will only be a good approximation when VDS over 2 is very much smaller than VGS minus VTH. Okay, let me discuss another consideration. Okay, so for the NMOS inverter, okay, what is the smallest input voltage okay that will result in linear operation. What is the smallest input voltage that will result in linear operation? Remember that we want to use this, or we want this to be in the linear mode when our input is a high voltage level, no? So for the high voltage level, or for VI equivalent to a 1, ano yung pinakamaliit na value ng VI na pwede? What is the smallest input voltage that will result in linear operation? Okay, the transition from saturation, or from linear to saturation, okay, this occurs when VDS is equal to VGS minus VTH. No? Again, if you recall, I drew this graph before. No? So this is linear, this is saturated, and this point is VGS minus VTH. No? So when VDS, this is VDS, when VDS is greater than this, it's saturated. When it's less than this, it is linear. Okay, anyway, so in this particular case, nandito tayo sa point na to, no? The transition from linear to saturated. Either the linear equation or the saturation equation will work because it is in the transition. What is the value of ID? ID is equal to 1/2 K VGS minus VTH squared. Okay, this is 1/2 K VDS squared, no? Because VDS is VGS minus VTH. Okay, but ID. Okay, anyway, let's feed in, no? So that's 1/2 25 VDS squared. Okay. But ID is also equal to this, no? 5 minus VDS over R, no? So 5 minus VDS over, I want ID to be in MA, so I'm going to use 0.5K. No? 500 ohms is 0.5K. Okay, therefore, I can equate now these two. No? I can equate these two. So 12.5 VDS squared is equal to 5 minus VDS over 0.5. No? This is M, this is K, so the two cancel. No? The two can cancel. Okay, so I have a quadratic equation that is, let's see, no? 12.5, that is 6.25 VDS squared plus VDS minus 5 is equal to 0. Sorry, I don't have the solution to this. Anyway, what will come out? No? Let me feed it into my calculator. Okay, so my first value is 0.817 volts. And my second value is an imaginary number. Of course, you cannot have an imaginary number solution, so this must be valid. Okay? So ito yung sagot natin. No? So VDS is 0.817 volts. No? So what is the corresponding input? No? This is VGS minus VTH, which is VTH is equal to 1. No? Therefore, VGS is now 1.819 volts. No? So this is my smallest. In effect, this is my smallest one. So I can even reconstruct now my transfer characteristic curve. No? This is going to be VO. This is going to be VI. Okay, for my inverter. So anything less than 1, my output is going to be VDD, no? Because anything less than 1 is going to be cut off. Right? When I am at 1.819, so this is to scale, no? This is 1.819. Ito yun. My output is 1.817, sorry, 1.817. My output is going to be 0.817, somewhere here. When I'm at 5, I already computed when I'm at 5, my output is 0.099. No? So dito sa 5, 0.1. No? So this is 0.10. Yan, at 5. So this is what my curve will look like. No? Okay. So here, this is equivalent to my 0. And here, this is equivalent to my 1. And note that when my input is 1, my output will be anywhere from 0 to 0.817. Okay. Which is pasok dito sa 0 to 1. No, sorry. Yeah, that's right. No? Pasok dito sa 0 to 1. Right? So let me just state that, no? When input is 1, output is anywhere from 0 to 0.817, and this is recognized as a 0. Because my 0 is between these two. Any questions? Okay. So again, no, we start with the inverter. The NOR is you just put a transistor in parallel, and that becomes a NOR. And your consideration now dito sa, by the way, this is also wrong. No? That's also wrong. Your consideration now dito sa transistor na to is whatever current flowing here will be shared here. No? So ganun din, no? If this is IR, this is IR over 2, and this is also IR over 2. If these are both conducting. No? For this particular input combination. No? So yung formula mo dito will not be like this, no? You have to divide this by 2 because it's going to be shared by these two transistors. Although if you want to simplify matters, you can just use the RDS on approximation. So this is using the RDS on approximation. And then again, the NAND, okay. This is wrong. The NAND, this is now in series. And then the complication of the NAND is the voltage here now, as you put more and more in series, will increase. And you have to make sure that as this voltage increases, it does not exceed this, no? It does not exceed the 0 level. Okay, I'm going to stop there. So I have an exercises here. I think these are also in the notes. So you just try the exercises on your own. Okay. Any questions? I might have gone a bit fast there, no? And I wasn't. Sorry, I was a little disorganized earlier. But if you have anything that you want to clarify, if it's going to take you some time to digest this, just send me email. No? If later on, after digesting it, there are things that you want to clarify. Okay, that's all for this afternoon. Okay,
Thank you po.
you're welcome.